We're taking a look at lesson 7.2 today. So the first thing I'm going to do here is find it in your class, and I'm going to go to classwork here. 7.2. I'd encourage you to open up a few things. Number one, make sure you take your attendance. This next thing is I will open up the pre-programmed graphs. I'm going to encourage you. I didn't show you much on parabolas, but I will show you some of that today. But ellipses in particular, and really the conic forms in general form, we're going to go over that graph. So I want to open that up for later. And of course, my formula chart. That's going to be like our best friend here for this chapter, especially for writing equations, which is what the bell ringer asked us to do. So I'm going to find our shapes over here for conic sections, and we'll get rolling. All right, so number one asks us to write an equation for a parabola that has a focus at 2, -5 and a vertex 2, -3. If you remember last class when we were talking over parabolas, I said, hey, here's what I know. When I'm writing an equation, I have what I think I've called it bare bones of an equation. Like I know there's a couple things that are going to be similar no matter whether it's a vertical parabola like this set of equations are, or a horizontal. And I understand the formula charts have changed throughout the years. They seem to rotate them all the time. So my laminated form doesn't look like the digital copy I'm showing right now. I'm hopeful next year they go back to the laminating. It was better, I thought. But anyways, what I want you to see is that both of these have some term squared equals 4p times another group, both formulas. So what I'm going to do here is I'm going to start off with that parenthesis squared equals 4p times the other parenthesis. Now, as I walked you through class solving for a parabola, we talked about there being 4 important pieces of information that we find, and I'm going to write them off. Well, instead of just saying B, I'll tell you it's the vertex, the focus, the axis of symmetry, and finally the directrix. Now, in this problem, they didn't really ask us to solve anything with that. They just told us to write an equation, but I'm going to write them out the way I normally do to show you, and let's plug in these points, how to solve. So our vertex was 2, -3. Our focus is 2, -5. Now I can see, looking at these 2 points, that's the y value that's been changed. And from the formula chart, if the y value is the one that's been changed, it's got to be over here. It's a vertical parabola. The way you get from a vertex to the focus is what happened is I've added a p-value. So what I did last class is I showed it this way, as I would say plus whatever the p was, gave me that 5. Oops, I didn't close that parenthesis. So the formula chart tells me that I'm adding a p. The formula chart also told me, since I realized it's the y value that changed, that x is going to be the value that's squared, y is the value that's not. So we could fill that in if we wanted to. We could put an x in this parenthesis here and a y in this parenthesis there. All that's based off formula chart. The fact that my y value changed. All right, so to solve this problem, let's go through and determine, back that up. Before I actually determine p, let's plug in the vertex into the equation. If my vertex is shifted right 2 units, what does that mean for my equation?
-2.
Good, because inside lies. Thank you, Taylor. Inside lies, so it'll be a -2. To shift right 2 on the inside with x, that needs to be a -2. What about to go down 3? You add, yep. Which now leaves us with only one more piece of information to solve. It's the p. How do I do that? I would just use this as an equation right here. The formula chart said that your vertex, the k plus p equal -5. Well, we know k is -3, so I'm just going to use that algebraic relationship. -3 plus p equals -5. All right, so I'm trying to isolate the p here. So what's the opposite of subtracting 3? You would add 3 to both sides. And we discover that our p is going to equal -5 plus 3 is the same thing as 3 minus 5, -2. Our equation wants 4p. So 4p would equal 4 times negative 2. What is 4 times negative 2? Negative 8.
Negative 8.
Yeah, there it is, negative 8. And so that's what we go right there, and we would have our solution. All right, so that's number 1. Though I told you it's not necessary, the axis of symmetry is by way of reminder, it's the value that doesn't change. So in this case, it's the x's that are not changing. So the value would be x equals 2. It's a line, and it would cut through. It would appear to be a vertical line cutting through the x-axis of 2. And the directrix follows this same relationship, but if you remember, you subtract your p, and it's going to be a y equals, since I'm dealing with y. So it'd be y equals negative 3, and I subtract the p value, which we found out p is negative 2. So I subtract a negative 2. So I have a minus a negative. 2 negatives back to back make a positive. So it would be negative 3 plus 2, which would equal negative 1. So that's how you get those pieces of information if you needed them. So I told you a few minutes ago that I would show you using calculators how you can get some of this information. If you go down to my parabola in standard form, I have mentioned that this is a vertical parabola because the focus value is next to y. If I click on vertical parabola here, and this opens up, we can test all of our information. I'm going to plug this in. What this means is my h, remember, is a positive 2. My h is a positive 2. My k is a negative 3. So I'm going to go to h here and put in a positive 2. And my k is a negative 3. Notice I'm not typing it into the actual equation. I'm typing it into the sliders. That way the math gets calculated for me here. Our p-value we got was negative 2. And so if I look down lower, and I'm not sure if these will, I won't show you the point. It's because I haven't labeled. But you can see that the vertex is at 2, negative 3. This says center. I need to update that. It should say vertex, but it's 2, negative 3. The focus is 2 units below that at 2, negative 5. You can see that's accurate. If you slide down over here, it says the directrix was negative 1. That's exactly what we got. And this doesn't show you, but the axis of symmetry would be the line x equals 2. X equals 2 would be the axis of symmetry. X equals 2. Sorry, x equals 2. I'll make it a dashed line so you can see it. That would be the axis of symmetry cut in half. So that was that calculator. You could use just to kind of, I guess, affirm your answers or anything like that. You could use that calculator there. All right, now let's try problem number 2. It says write an equation for a parabola with a directrix of x equals negative 4 and a focus of 12, negative 2. Okay, I'm going to start this problem the same way I started the last one. What did I do first from the formula chart last time around? Do you remember? Yeah, I took the bare bones of the problem, the parentheses of the problem, if you will. So I took this, or from the formula chart. So parentheses squared equals 4p times another parenthesis. And then I mentioned that in class we were finding 4 things: the vertex, the focus, the axis of symmetry, and the directrix. I said, you know what, we're not going to have to find all of these, but I wrote them out just like I did in class. On this particular problem, if I wanted to fill in my values, I have x equals negative 4 for a directrix and a focus of 12, negative 2. All right, if I want to go through solving this problem, I'm going to go see if the formula chart can give me any answers away. And the answer is going to be yes, it can. When I look at the formula chart under parabola, you'll notice on directrix in particular that one equation has y equals, your other equation has x equals. Obviously, since we have x equals negative 4, we are going to be using this parabola. This is going to be a horizontal parabola because the focus is next to x. So the equation is going to be in this order, where this will be our focus, this will be our directrix. So I'm looking at this set of equations here. And I know if you're here looking on my formula chart, they're flipped around. I understand that. So, but for the digital copy, this is what we have. So I'm going to put y on my left parenthesis. Y is the quantity being squared over here, and x is in my right parenthesis. So we just established that. The other thing we can establish is that the focus is going to be in the form of h plus p comma k. So the focus is equal to h plus p comma k. So I'm going to just take the k. We can see k is -2. So when I plug that in over here with y, because k goes with y, you make it a lie. So it'll be y plus 2. Okay, so how did I get that? Just said the k is -2. If k is -2, then when I replace it with the y, it just becomes a lie. Now, this also implies that h plus p equals 12. So I'm going to write that down. H plus p equals 12. Now, I have two variables. You can't solve two variables with only one equation. So I'm going to come back over and see about this directrix again. What does the directrix tell me? Well, the formula chart says that x equals h minus p. The formula chart says x equals h minus p, which means h minus p equals -4. That's my second equation. H minus p equals -4. What you learn in algebra is that if you have two variables you need to solve for, you need to have two equations. Now we have two equations and we can solve. I'd like to use elimination technique here. I have two equations. If I combine these equations together, notice that my p's will eliminate one another. I have a positive p and a negative p. Those will simplify or cancel each other out. So it has, what I'm left with is h plus h, just two h's, equals, these get simplified. I'm going to take that away just for a second. I'll show you why. Those get simplified. Equals 12 minus 4. What is 12 minus 4? 8. Good. So when I divide by 2, our h equals 4. Now, h goes in with x, but it goes in as a lie. So it's going to be x minus 4. That's because the formula says that it's x minus h, and the k is y minus k. That's why they go in as lies. It's right there. All right, last thing to solve is p. If I want to find p, now what I can do, since I no longer have two variables, I only have one, is I can come back to one of these equations. Let's say this one. And we'll plug in with h equaling 4. So we'll have 4 plus p equals 12. You could have chosen either of the equations, by the way. I just chose the first one. 4 plus p equals 12. How would I isolate the p here? It's subtract. There we go. It's adding, so we need to subtract. Do the opposite. We find out p equals 8. The equation calls for 4p. So 4p would equal 4 times 8. I'm getting 32. So we can say this right here is 32. And that would be your answer. Again, you could check this with my calculator I created. I'll go quickly here. It's a horizontal parabola because the focus was next to the x. We had that the h value was 4, the k was -2. So h is 4, k is -2. We got that p is 8, if I remember right. P is 8, yes. So when I look at my formula, you can see the center is right 2, down 1. We didn't ever find the vertex, but that's where it would be. It would be right 2. Down. That's not accurate. What did I do wrong here? The center. Oh, I was too zoomed out. Sorry. It's right 4, down 2. It's right 4, down 2. Desmos was counting by 2s on me. Right 4, down 2. Down 2. That would be the vertex. You notice the p would be 8 there. The value that does not change is the axis of symmetry, the y. Y equals -2. And that would fill in that information as well. You can check over here, directrix is x equals -4, so it did do correctly. All right, so that's just how those calculators are there for you if you want any help in that regard. With that, I'm going to close off lesson 7.1, and we're going to take a peek at lesson 7.2 now. So 7.2, we're dealing with, in particular, ellipses and circles, but today we're going to really spend more time on ellipses, okay? Circles are pretty basic. We're going to spend the majority of our time with ellipses. So there's a few vocabulary terms I want you to be aware of. So let me give you an ellipse here, or an oval as some people call it. There's an oval. Here's the terms that you'll see. The center of an oval or ellipse takes the name center. Nothing spectacular about that. Every oval will have two vertices. That's the plural for vertex. So the farthest point from the center is a vertex. And in every ellipse, there will be two of these, or every oval, there will be 2 points that are equally as far apart as any other. So these two are my vertices because it's plural. So you don't say vertexes. Almost sounds like we're talking about Texas, but with a ver in front. We don't say vertexes. You would say vertices. That's the plural. So there's one vertex. There's two vertex. Two make vertices. Okay, that's the farthest point away from the center. The closest point to the center is called a covertex. Once again, because of the shape, there will be a point on the other side that's exactly the same distance away. It would be the other covertex. Two covertexes would actually be called covertices. You'll see me abbreviate CV today. There are two focuses. It's hard to say, so they don't call it focuses, they call it foci. Two foci. They will be on what you'll learn is called the major axis. They will be in line with the center and the vertex, and the vertices, I should say. They will be on that straight line. So you'll have two of those. You'll have the term major axis. Major axis connects vertex to vertex. And you'll have a term called the minor axis, which will connect covertex to covertex. And that will be all your points here. Well, I can't quite get it centered, but it is what it is. All right, so the math, if you want to write them on there, the major axis is going to be, it's very important that you get this down. The major axis is the length from vertex to vertex, from vertex to vertex. So from vertex to vertex, vertex to vertex. That's going to be the value 2a. You're going to see the equation in a second. It's going to be equal to 2a. So you can put 2a there. From vertex to vertex, which will equal 2a. The center is the hk. Center is the h comma k. The minor axis is from covertex to covertex. So from, I'm going to run out of room, so I'm going to just say cov to cov. Looks like COVID. Cov to cov, which will be equal to 2b. The vertices, like I told you, the part farthest away from the center. The covertices are the points closest to the center. And the eccentricity is going to be a measure of how elliptical it is. Okay, so there's a lot of the math. Let's get going. There's your diagram. All right, and here's another one just given to you with just some general rules for the different shapes. Let me make sure I'm on my formula chart here. We're looking at ellipse. Notice the only things different in the two ellipse formulas are the a squared and b squared values. On a horizontal, the a is always the larger number. A horizontal, the a squared will be under the x squared. On a vertical ellipse, the a squared will be under the y squared. So that's how that'll be the only difference. But let's talk about how to graph these. So graphically, you first would identify the center. And the center you can find by looking at the h and the k, the values with x and y. So on this one, remember, inside lies. So we're going to say that x plus 2 is actually going to shift to the left 2 because inside lies. So it's going to go left 2, and the y minus 1 is actually going to send us up 1. So my center will be left 2, up 1. That's the center of my ellipse. I'm just going to use a C for center. So my center is -2, 1, HK. Now the values underneath refer to a squared and b squared. A squared is always the larger one. So in this problem, a squared is 9 and b squared is 4. So if a squared equals 9, that means a is going to equal 4. And we're going to learn that you don't do plus or minus when you take the square root here, because it's going to be distance. So distance is always positive. So I'm just going to treat it as the positive answer. And b squared is 4, which means b equals 2. So what does that mean graphically? Well, because a squared is under x, what that means is I'm going to go, since a is, why did I put 4 there? No one corrected me. That is bad, terrible math. What number should I put right there? 3, thank you, 3. What that means is when I plot my vertices, I'm going to go left 3 and right 3. You go the square root of what you see. So I'm going to go left 3, 1, 2, 3. That's a vertice. And I'm going to go right 3, 1, 2, 3. That's another vertice. One vertex, a second vertex. I see a 4 here, but that's b squared. When I take the square root of that, I get 2. Since it's under y, I'm going to go up 2, 1, 2, co-vertex, CV, and I'm going to go down 2, 1, 2. Go vertex. I'm going to put a CV there. My ellipse will go through those 4 points. Ellipses aren't the easiest to draw, so I'm going to use this tool right here. Why is that I don't want there to be a fill on that. Let me go here. Properties. I clicked the wrong one. I wanted to go no fill, but the line I wanted to have color. There we go. That's what the ellipse would look like right there. So it asks us to graph it. There it is. If I was going to label some points for you, the vertices, again, the vertices are the points farthest away from the center. They would be left 5, up 1. And this other one is a right 1 unit, up 1 unit. The co-vertices are the points closest to the center of the circle, which from the center, it looks like they're down 2, or left 2, down 1, left 2, down 1, and left 2, up 1, 2, 3. Those would be the co-vertices. Now, I know this problem didn't ask for any of that information, but I'm just giving it to you. And also, so we don't forget, the major axis would be the length from vertex to vertex. So the major axis is the length from vertex to vertex, which will always equal 2a. So 2 times 3 is 6. So this would be 6 units long. And if you count it, you'd see it's 1, 2, 3, 4, 5, and 6. Okay. Minor axis is always the shortest distance across an ellipse that goes through the center. It's the shortest distance across that will pass through the center. And this one would be 1, 2, 3, 4. 4 units. It's always 2 times the b. The last thing, though, I'm not going to find on this problem, well, maybe I will, is if you wanted to find the foci. The foci are the reflective points. And I'll get to why it's important as we go on. But the reflected points, there is a formula on the chart that says there's an ABC relationship. Oh, the foci is right here. You use the value C for that, but you don't see C. You don't see SEE, the letter C, in the equation, but you can solve it using this relationship to find the foci. And so to find the foci, you use the formula C squared equals A squared minus B squared. Very similar to the Pythagorean theorem, but with a minus. And so in this problem, I would plug in my numbers 9 minus 4. C squared equals 9 minus 4, which is 5, which means C equals 5. The foci, the square root of 5, I'm sorry. The foci on this problem would be located plus or on the major axis, so it'd be left and right, square root of 5 units from the center. So it's kind of weird how to write this. So let me just show you like this. You could say it's from the center, which is left 2. You would say left 2, and you would either go right to the square root of 5 or left to the square root of 5, and all the while being up 1. So square root of 5 is a little bit bigger than 2. It's going to be a decimal, so I'm just going to roughly plot a f there, and a little bit more than 2, plot an f there. That would be the foci. That's how you'd find that. So this problem only asks us to graph it. I did way more than graph it, but there is all the information you might ever need for an ellipse right there. So now let's take a look. What happens if it's not in standard form? So this is standard form. What if it's in general form? Well, if it's in general form, and by the way, I need to back up. I do have calculators for these. Let me go one more time very quickly. If you're on ellipse in standard form, you can graph it. Just make sure you understand how the sliders work on Desmos. You don't type in the equation like this. If you want to be able to find these pieces of information, you need to use your sliders. So for example, we said our h was -2 and our k was 1. So I'd go -2 and 1. We had a being 3 and b equaling 2. And so there's my ellipse. And notice all these other values could be found for you. So there was the center. If you the foci are here and here. You notice they're just past where we place it. It's like -5.24, 1. On ours, if you looked at it, it's just, did I type something in wrong? I did. That's supposed to be a -2. There we go. If you look closely at this point, it's just past, it's like -4.2 basically. If you look on here, it was just past -4. So it did do it correctly. All right, so if you ever need to find anything, you can use that calculator as well. All right, now let's go to part B. What if it's in general form? General form, do you have a calculator for it? Yes, I do, but I'm not going to solve it first with calculator. I'm just showing you I do have a calculator for it. How would you solve this by hand? Well, we talked about general form last class, and for parabolas, the key that like before we started, I said there's going to have to be like a pre-step where you separate your x's and y's. On ellipses, you don't separate your x's and y's. On ellipses, what we need to do is let me get the equation. We don't separate the x's and y's. We need to have x's and y's on the same side of the equation, but we're going to get the number by itself on the right. So my pre-step here is I'm going to get the number here, the -3, by itself on the right side. So that's like my pre-step. So what will I have here? 4x squared plus 24x, and I'm going to leave a gap. And then I have a plus y squared minus 10y, I'm going to leave a gap, equals 3. And I just did this because we're going to have to complete the square. You may remember it from last class, completing the square. We're going to have to do that for both of these, the x value and the y. It's the only way we can get a square in terms of a perfect square like we see in these equations. Whoops, like there are 2 perfect squares. So I done my pre-step. Now I go into my 4 steps that we learned last class. Step 1 was to divide by something. What do we divide by? That's going to be the next step, actually. It was divide by the a. Now, here's what's different for ellipses and hyperbola, is that when you're dividing, you're only going to divide out of the front portion, and then you'll do the same on the back portion. You'll divide out a over here as well. So I'm going to first look on this front grouping, the grouping of x. If I divide out a 4, I need to divide out this 4 as well. So what I'm going to have is I will have a 4 out front. It's kind of like a GCF. Let me put that in parentheses here. GCF is really what it is I'm going to have parentheses x squared plus 6x plus that blank. Plus, now over here, there's nothing to factor out. You could put a 1, but there's no number with the y squared, so I don't need it. So I'm just going to say y squared minus 10y with the blank equals 3. And I should have done this before. There's going to be 2 missing numbers. So I'm going to have 2 blanks here. Blank 1 and blank 2. You might be going, why are there 2 blanks? Well, because I added 2 blanks on the left. If I've added 2 blanks on the left, I'm also going to have to add those same 2 blanks on the right. So I should have done that on that step as well. So let me add that. So we have those blanks. Okay, that was step 1. Who remembers what step 2 was? You take your b and you divide it by 2. So b gets divided by 2. And you're going to do this for both trinomials here. So I have a positive 6 divided by 2. What is positive 6 divided by 2? 3. I put a plus there. You'll see why in a second. Okay, I'm going to go to the second grouping before I move on to step 3. I take my negative 10 and divide that by 2. What is negative 10 divided by 2? Negative 5. All right. We come back over here. What was step number 3? It was we take our b and we square it. So I'm going to take, the b over 2 and square that. So I'm going to square this positive 3. What's positive 3 times positive 3? 9. Okay, so normally we think, okay, I added a 9 on the left side. I need to add a 9 on the right side. What's a little bit different though is this 4 is going to actually multiply times 9. So what I need to actually add over here to keep this accurate is a 4 times 9. Again, the reason why is I'm not just adding 9. I'm ultimately adding 36. 4 times 9 is 36. I'm ultimately adding a 36 on the left side. So I need to add a 4 times 9 of 36 over here. Now I'm going to do the same thing on the second parenthesis, or second group here, the second trinomial. What is negative 5 times negative 5?
25.
Positive 25. And so that's what goes here, positive 25. Now this 25 does not get multiplied by anything. So it'll just be 25 on its own out there like that. Which brings us now to step 4, where we simplify. So the whole point of going through a complete the square is it creates a perfect square, a perfect trinomial. If you think about factoring, factors of 9 that add up to 6, it's going to be positive 3 and positive 3. You're going to have 2 of them. So factors of 9 that add 6, it's going to end up being this trinomial is going to factor as x plus 3 times x plus 3. So it becomes 4 times x plus 3 squared. The shortcut is I'm dealing with the variable x. My numbers are plus 3 there. It's x plus 3 quantity squared. Over on the second trinomial, factors of 25 that add up to negative 10. Well, that would be negative 5 and negative 5. So once again, I have a perfect square. It'll be y minus 5 squared. And all of this would equal, let me go to the calculator here. All of this will equal 3 plus 4 times 9 plus 25, which is 64. Okay, I'm not done simplifying. To get it into standard form, we are really close, but standard form has each grouping of x squared and y squared being divided by some numbers. So what I need to do here is divide by that 64 to set it equal to 1. So part of this simplification process is we need to divide this by 64, and then we should have our solution. I can reduce this. 4 goes into 64 16 times. If you didn't know that, you could go over here to the calculator, type in 4 divided by 64 and hit this fraction, and it says it goes in 16 times. So I have here, it's going to be x plus 3 over 16 plus y minus 5 squared over 64 equals 1. And that's our solution right there. There's our equation in standard form. If we were going to graph this like it says to do, on your next slide, you'll see you have this graph. Let's graph this equation. This is telling me to go left 3 units, left 3, up 5, because inside lies. So left 3, 1, 2, 3, up 5, 1, 2, 3, 4, 5. And that's our center. I'll put C for center. I'm told the value underneath the x is the 16. That's b squared. I know it's b because it's a smaller number. The square root of that here, if that's b squared here, you have b squared equals 16, then b equals 4. I need to go left and right 4. 1, 2, 3, 4. That would be a covertice. 1, 2, 3, 4. Covertice. Those are going to be the closest points. Also meaning my minor axis would be a length of 8. 4 and 4 is 8. Over here, I can establish that my a squared is 64, meaning a is 8. My vertices would be up 8, down 8. So 1, 2, 3, 4, 5, 6, 7, 8. It'll be floating off somewhere up here as a vertice. And then down here, 1, 2, 3, 4, 5, 6, 7, 8. This would be my other vertice. Since I went up 8 and down 8, for the record, your major axis would be 16. And your ellipse would look like that, give or take, something similar to that. I told you I had a calculator for this. So now using this calculator, how could we have done this from the start? If you have your equation, the way to use mine is you have to use the slider. Don't try to type them in up to the equation line because it won't solve all the math that you might need solved with it. But we have, I'm going to go off of this order because this will not always be given the same order as I have written up here. My a is how many x squareds? My coefficient over here is 4. So my a equals the coefficient 4. B represents how many x times y's I have. I don't have any xy, so I'll leave that as 0. C is y squareds, which I only have one of those. 1y squared. My D is however many x coefficients of x I have, which is 24. E represents the coefficient in front of the y, which is -10. And F is the number on its own, the constant, which is -3. There's our picture. And again, you can go to key attributes and find out a lot of this information, that it was shifted left 3, up 5. The A goes up 8 and down 8, meaning as a squared would be 64. B goes left 4, right 4. So it would be a 16 there for a B squared. And any of the other values that we're going to look at today as we go. All right, so there it all is for you using calculator. With that being said, I'm going to give you your first DOL. You can use your algebra. You can use the graphing calculator if you so desire. But I want you to graph and see which graph is the answer to this conic section here. DOL number 1. Now let's take a look at example 2 here. It says write an equation for an ellipse with a major axis from 5, -2 to -1, -2, and a minor axis that extends from 2, 0 to 2, -4. All right, I like these because with ellipses, the algebra is about as simple as any of the shapes. So we have to write an equation. So kind of like we did on the bell ringer, I'm going to write out the bare bones equation for a ellipse. And so I'm going to let you see them just for a moment. When you look at these two equations side by side, you'll notice that there's a lot in common. The only thing that's different is where is the a squared and the b squared located. That's the only thing that changes. Other than that, the equation stays the same. So I'm going to have an x plus or minus some value squared divided by some amount plus y plus or minus some amount squared divided by something equals 1. That's what I know I will have. So I'm going to write that part out. I'm going to call that the bare bones. Now, they said major axis, and I like noting the vocabulary each time around. That really helps, I think. And major axis is 2a. Okay, anytime you see major axis, that means 2a. It goes from 5 to the right, 2 down. 1, 2, 3, 4, 5, 2 down. By the way, I've had great questions about when do I know inside lies and something's telling the truth? Well, if it's in a parentheses with the variables x or y, it'll lie. But this will not lie because it's not in with the variables x or y. So it's 5 to the right, 2 down. 1 to the left, 2 down. Those are that's the major axis. So major axis is technically a line, goes from here to here. But a major is always your vertices. So vertice there, vertice there. Okay, question. How far apart are those? This one's left 1, this one's right 5. How many units apart is left 1 to right to 5? 6. So we can say that 2a equals 6, which means, whoops, started to write the answer. If 2a equals 6, then a equals 3. Not only that, it's going left and right. So when I plug in my equation, I need to put a squared equals 9 going left and right, meaning under the x. So I put that there because it goes left and right. Now we established a is 3, which means that we can now find the center. The center is 1, 2, 3. That's going to be the center right there. The center was 3 away from either vertex. So the center, it's 2 to the right, 2 down. 2 to the right, 2 down. That's h and k. When I put it in this parentheses, inside needs to lie. So it'll be x minus 2 and then y plus 2. All right, back to the problem. It said there's a minor axis from 2, 0 to 2, -4. So minor axis, anytime you see that, I want you to think 2b. It's from 2, 0, 2 to the right, 0 up. That's a co-vertex. To 2, -4. Sorry, I wrote that too big. So that's the center. I'm not going to label the center any longer. It just takes up too much space in there. So there's my co-vertex. All right. Co-vertex are always on the minor axis. That's how I knew that. So if the co-vertex is 2 up and 2 down, that means 2b equals 4 or b equals 2, which implies b squared equals 4. And we have our equation. I didn't show the algebra here, but 2b equaling 4, you divide that by 2. To get the value 2. And that would be my equation. All right, let me give you another here. Part B says write an equation. Again, if you're writing an equation, I would recommend getting the bare bones, which is some quantity of x being squared over some number, and some quantity of y being squared over another number equaling 1. So I'm going to start there. It says vertices at 3, -4. So write 3 down 4. By the way, a vertice is going to be the value. It's going to be with a because it's like a major axis length across. So the other vertex is 3 to the right, 6 up. So we could calculate our major axis and our a value from this. So really quickly, it looks like this vertex is down 4 units. This vertex is up 6 units. How many units apart are they? If this one's down 4, this one's up 6. 10. So that means the major axis equals 10 in distance. And so what does A actually equal? 5. And then what would A squared equal? 25. Okay, so that 25, this time it's vertical, which means it's going up and down. There you go. A squared is 25. Since it's going up and down, that's going to go under the y squared term right there. Also, since we know that A is 5, we could find the center. 1, 2, 3, 4, 5. That's the center of the graph right there. It's going to be our center. And so we could say it's going to be right 3. So x minus 3. So let me write that down. Center is right 3, up 1, which means it's going to be x minus 3 and a y minus 1 like that. Finally, it says foci are 3 to the right, 4 up, 3 to the right, 2 down, 3 to the right, 4 up. There's a foci. And 3 to the right, 2 down. Okay, now we get to use the foci. So on example 1a, I did briefly show you how the foci works. Let me now walk through it. So over here on the formula chart, you'll see that foci is from, depending on which formula we're working on, and since this one, we don't know, well, yeah, we do know that it's a vertical because the vertices are going up and down. The foci is following this formula, which means the foci are plus or minus c units away from the center, plus or minus c units away. So because my foci are up and down 3, I can say c equals 3. So that's from my foci. It's c equals 3. Now c equals 3, what I'm going to now do is go back over this formula chart and realize that my b value I need to find, I can use the c squared equals a squared minus b squared formula right there to solve for the b squared we're missing. So c squared equals a squared minus b squared. That's the relationship between the 3 variables. It's kind of like Pythagorean, but with a minus. On this problem, we know c, if c is 3, then c squared equals 9. So it'll be 9 equals 25, that's a squared, minus b squared. And all I have to do is get b squared by itself. So if I subtract 25 over, we have that negative 16 equals negative b squared. And if negative 16 equals negative b squared, what does positive b squared equal? Positive 16, that's right. So positive b squared would equal positive 16. That's all that the formula wants is b squared. So you can just put a 16 there. If you want to find b, you could say b equals 4, but you don't have to actually have that 4 there. And so that would be my answer. All right. Could you check answers with calculators? Sure. But these I would recommend using formula charts and a little algebra. That's what I would recommend on these problems. All right, here is DOL number 2. Again, I would just plot these points. You might not have this graph at home, but I would just try to graph it. Just create your own little graph, create those points, put the major axis, and honestly, you can solve the whole problem right from here. Believe it or not, you can, given the multiple choice answers. But even if you didn't have multiple choice, you could solve the whole thing with using both of those. So go ahead, plot those, see what you come up with. DOL number 2. Now let's talk about eccentricity. So I told you earlier, eccentricity is the measure of how elliptical an object is. And so the eccentricity can be arranged really 0 I need to check this, but the way I remember it anyways is that the eccentricity of a circle is 0. The eccentricity of any type of ellipse is something between 0 and 1. So this is when the eccentricity would be between 0 and 1. If it hit 1 exactly, it would be a parabola, if I'm right in my thinking anyways. Let's do a parabola. And that's when the eccentricity equals 1. And then if eccentricity gets greater than 1, it becomes a hyperbola. I believe that's the way it looks anyways. And so that's the relationship for eccentricity. We could Google it to double check. Eccentricity. And you could look off of here the values. Let's see if it tells us really quickly. Parabola equals 1, hyperbola is greater than 1, circle is 0. Yep, got that right. So that is correct for you, okay? So the relationship for the value is E equals C divided by A. That's how you find that, all right? That's the mathematical concept of getting to eccentricity. Astronomers use this, as we'll see in their problem, to measure orbits, okay? So 0 is not safe if you think about something like if this is the sun and you wanted something to have a circular orbit, it's not going to last very long. Or like if we launch a satellite off our Earth and try to make it a circular orbit, it won't last very long because Earth's gravity would pull it in and it would kind of just spiral in until it crashes, if that makes sense. So that would not work. Nor would it work if this was the orbit. You know, it goes around, here's the, let's say, whatever you're orbiting around, it goes around and then it takes off forever. That wouldn't work either. So either you die by if you get sucked in, or you die because you get thrown off forever. And so really the sweet value for people trying to keep things in orbit is a value 0 and 1. That's what you're looking for. So here's example 3. It says determine the eccentricity of this ellipse given by this. Now, I'll tell you cheat. This is where my calculators do really well. If you just graph this, eccentricity is a key attribute that's listed in there, and it would give you the answer. So I'm not going to just cheat. So I'm going to go through here. Remember, the relationship was C divided by A. So how do we get our C? Well, I'm going to start with knowing that the relationship for C is that C squared equals A squared minus B squared. And I'll go back to that formula chart in a second, but I'm just going to tell you right now that 64 is the A squared. It's the larger value of the two, so that must be A squared. B squared is 36. So the relationship, let me show you again from the formula chart, is that C squared for any ellipse, C squared equals A squared minus B squared. So let's solve for our C squared. C squared equals A squared minus B squared. So when I plug in my formulas, C squared is going to equal 64 minus 36. I believe that number is 28. Just say that's 28. I think it is. So C would be the square root of 28. And I'm going to reduce that. The reason, if you were listing this answer as a decimal, you wouldn't have to. You go to your calculator and say, all right, I know that C is the square root of 28, and A is the square root of 64. So A is, let me put that there, A is 8. And say, okay, it's the square root of 28 divided by 8. Well, mathematically, that is true, but that could be reduced. And so how can I reduce it? Let me start with the square root. 28, if I did upside down division, a prime number that goes into 28 is 2. 2 goes in 14 times. And a prime number can go into 14. What prime number can go into 14? 2. And that goes in 7 times. This would be my final answer, where I have a pair of 2s. So what that means is the pair comes outside of the square root. The single goes back inside. So the square root of 28 is equal to 2 square roots of 7. So 2 square roots of 7 divided by 8. And we could reduce that one more time. 2 goes into 8 4 times. So it was the same thing as square root of 7 over 4. That would be the value, the exact answer for your eccentricity. Now, you might have heard me say something about calculators, and you're thinking, Mr. Voorhees, how do I do that? Well, if you're on your Desmos, this equation is an ellipse in standard form. So if you go to ellipse in standard form, and we type in our values, remember inside lies, so the h is going to be 4, k is 3, h is 4, k is 3. The a squared, we had 64 there, which means a is the square root of 64, or 8. I had 36 here, which means b is the square root of 36, or you could just put 6, whichever one you wanted. So there's my problem. If I go down to eccentricity, click that, it tells me this decimal. And if you checked square root of 7 divided by 4, you'll notice that's the exact same degree measure, or not degree, I'm sorry, decimal measure. So that is correct. So you can use my calculators for this, whichever way you want. All right, so that was my problem. Now it's your turn. If you want to use my calculator, notice this time the one difference you need to make is this is not standard form. You would need to use this formula or this calculator right here, conics, and general form. This is general form. If you want to not go through the math, you would use this format to solve your problem. DOL number 3. All right, now we're going to take a look at example 4. But before I really work through this problem, I want to show you something that I think is just remarkable. This is talking about astronomy, and I'm going to kind of give you an idea of how this orbits work. And so orbits truly are ellipses. So a lot of people think of orbits being circular, but they're not, as I kind of said a second ago. So I want to just give you a little visual diagram here. Let's say we have the sun here at the center of our galaxy, and the galaxy is just this big white space. And the first planet that we know that orbits around the sun would be no one knows, Mercury. Okay, so there's Mercury, and let me give it an orbit. So the thing about orbits is they're not actually circular. They are elliptical. There's an old trivia question that said, when is it most cold? Or why is it most cold during the winter? Is it because the sun or the earth is farther away from the sun? And you're like, no, you learn it's the tilt of the earth. Well, that riddle, if you will, is based off of a common theme that the orbit is circular, but you kind of understand with that riddle, no, wait, if there's a time when it's closer and a time when it's farther, it's not circular. It's got to be elliptical. And they call those terms the perihelion and amphibian, or I don't even know how you pronounce it, but that's what they call the terms. But anyways, here's what we have so far. Here's my sun. Here's Mercury. Not going to write Mercury because it won't travel with it. And notice I didn't put the sun at the center. There's a reason for it. Next planet. So what's the next one after Mercury? Who knows? I hear Venus. We'll make Venus be red. So I'll put Venus right here. There's Venus. Okay, what comes after Venus? Not Mars. Earth, there it is. Earth. And I'm going to give Earth a little rotated one. Let's do it like that. There's Earth's. And so I'm going to make Earth's little sphere here be blue with, I'll do green on the outside. So we know, no wait, what did I say? Green on the outside, blue on the inside, because it's mostly water. So there's Earth. We'll make Earth a little larger. And so there's Earth. And I'll do one more here. And then I'll get to my point of what I'm going to say about this, what I find absolutely remarkable. Okay, and so we'll do one more here. Now comes Mars. So I don't know what color to make. I'll just do it purple, this purple color. All right, so there's Mars. So we have these planets. And what we know is true in the solar system is that these planets are traveling around. Like, for example, 1 year is how long it takes the Earth to make one trip around its orbit, right? And 1 day would be rotating around one full time, like that. 1 month, for the record, is that the moon, as the Earth goes, you have a moon making its own little orbit around Earth. And so let me fill it with white, but make it black. Okay, there we go. Here's the moon. 1 month, if you're wondering, is 1 trip around for the moon. Okay, so there's a month, there's a day. This would be a year, except we wouldn't leave our moon behind. So anyways, that's going on. Let's just say the Earth is rotating, orbiting this way around the sun. Well, Mercury may be orbiting this direction around the sun, but it may be rotating the same direction as Earth. So it's going around the opposite way, but it's rotating the same way. And I'm not actually sure which one goes which way and all that. And plus, this is only 2D, and it's actually 3D. Well, Venus might be orbiting this direction, but it might be spinning the opposite way of Earth. So Venus and Earth may be orbiting in the same direction around the sun, but they might be spinning backwards. Mars is orbiting the wrong way, but spinning the same direction as Earth. And then maybe you have Mars that is on a whole different spectrum, like 3D spectrum, pulled out, orbiting totally different, spinning just the same as one or the other. And it's crazy. What's true about all of these is the sun is not at the center of any of these orbits. Do you know where the sun is located? No one knows. Of course you don't. That's why I'm telling you. It's located at the focus on every single one of these orbits. The sun is exactly at the focus. If it's not at the focus, what happens is that eccentricity gets off. And if you're too close, let's say it's circular, what happens is the planet would get sucked in and it would burn up and you would never have that planet. If it got too far away, if it was too far off the focus this way, what would happen is the planet would come around and it would pick up so much speed because of the gravity, it would get slingshotted off and it would disappear and freeze to death. All this only works because they're perfectly located with the sun being the focus of all of these. I think this is absolutely remarkable and worth looking into. I'm not supposed to tell you what to believe, and I'm not going to tell you what to believe. But when I heard this, I thought in my mind, there is no way an explosion created all of this. But find a better explanation. I'm not going to tell you what to believe. You put the explosion creating this, all that order and craziness and randomness comes from explosion. I think not. I think it's pretty wild. It's something to think about. It's really crazy. So figure that one out and come back and talk to me how it happened. Anyways, with that as the groundwork, let's look at this example 4 here. It says, in astronomy, the eccentricity of an orbit of Uranus is 0.47. Again, that's just the measure of how elliptical it is. So however elliptical 0.47 would look. So a circle, if I had a circle, that's 0. And if it became so skinny like this, it flew off, that would be 1. So this is ultimately going to be elliptical, but it's, it's not going to be circular either. So circle will be 0, 1's a parabola. So it is an ellipse, but it'll be, I don't know, maybe not quite that wide. It might be more something like this. So I'm just going to guess and say there's Uranus orbit. And it orbits around the sun. So like I was just walking through, if I was going to draw this properly, I would need to put the sun out of focus. So let's just put a sun right there and say that's the focus. And you'd have your planet somewhere else. Okay, on this, it says it has a major axis length of 38.36 astronomical units. So the major axis is the distance from one vertex to the other vertex, which is the farthest distance apart from the center. So that length from there to there is 38.36 astronomical units. And by way of reminder, the major axis is always 2a. So 2a equals 38.36 astronomical units. We could solve for a. So our a, if I'm doing my math right, 38 divided by 2 is 19. 36 divided by 2 is 18. Our a is 19.18. Are we cool with that? All right, and now it says, oh, I forgot something, the eccentricity. The eccentricity, the formula chart says eccentricity is c divided by a. So one of the things I don't like about the released formula chart they had this year is it looks like eccentricity only belongs to hyperbola. It should have a line going all the way across. Eccentricity belongs to every shape. It's c divided by a. So our eccentricity is going to equal c divided by a. And they tell us the number is 0.47. So I'll put that right there. 0.47 is C divided by A. Well, now that I know what A is, I can just say 0.47 equals C divided by 19.18. See what I did there? Just substituted in the A. So what can I do with this? Yeah, we could solve for C by multiplying. Right now, C is being divided by 19.18. We could isolate it and solve for it by multiplying by 19.18. So if I multiply both sides by 19.18, I should find out what C equals. Go over to Desmos. Let's just get a blank graph here. So I have 19.18 times 0.47. I get 9.0146. 9.0146. And by the way, this would be in astronomical units. Units hadn't gone away. They haven't changed. That distance, by way of reminder, that would be from the center here to the sun. What we just solved for is that distance right there is C. That's what that is. Okay, but it says, what is the length of the minor axis? So we're trying to figure out this minor axis, which happens to be 2b. So the minor axis is always 2b. That right there is 2b. So if I want to solve for b, given a and c, you need to use this relationship that we have on the formula chart. C squared equals a squared minus b squared. So what I'm going to do here is I'll say c squared equals a squared minus b squared. And so basically my values, when I plug these in, will be 9.0146 squared equals 18, or a squared, which is 19.18 squared minus b squared. We'll subtract the 19.18 squared. And I'm going to see what I come up with. So it's going to be 9.0146 squared minus 19.18 squared. It's negative 286. So we have negative 286 point, I'm just going to say 61, is approximately negative b squared. Now if that's negative b squared, then positive b squared, let me make it a little white space here. Then positive b squared, since those are both negatives, positive b squared would equal 286.61. And we could take the square root. Now we don't have to do plus or minus because it's talking about a distance. So we know it's going to be positive of it. So I'm going to go square root. And I'll take a few more of these decimal places while I'm here. 60938.684. That's my b. b equals approximately, so I'll just do this squiggly because I'm not going to write it all down, 16.93. And this again would be in astronomical units. And so if I needed the minor axis, then the minor axis would equal 2 times it. So minor axis equals 2b, which equals, if we multiply that by 2, just multiply this by 2 times, I get 33.86. Now I should do a squiggly. 33.86 astronomical units. And that would be my answer there. So that one got a little crazy because of those decimals. We didn't have very good help. Whatever is the explanation for the creation or the universe or whatever it was, whether it be your explosion or something else, they certainly could have given us better numbers to work with. Now you have DOL. Yours would be very similar, but prettier numbers at least to work with, not the decimals. So go ahead and try your elliptically shaped lake. So I'm going to give you an idea here, elliptically shaped lake. And I want you to solve knowing that the length of the lake, the length here, the reason I'm helping you out is because it's going to use a lot of vocabulary we haven't. The length is referring to the major axis is 2,500 meters. It's 2,500 meters. And the width is 1,500 meters, which would be the minor axis. So I'll give you a hint there. That's going to be your 2A, that's going to be your 2B. And you need to solve for the eccentricity using your formula E equals C divided by A. So that's your 2A, that's your 2B, and I'll let you go from there. All right, now let's take a look at a circle here. The standard form of a circle has the equation x minus h quantity squared plus y minus k quantity squared equals r squared, where r is your radius. So let's take a look first at a general form. So general form, again, as you just saw over here, the x squared and the y squared are going to be together, and what's going to happen over here is it's going to be a number value. The radius is a constant. It's going to be on its own. So what I'm going to do first for the pre-step, if you will, is I'm going to add 32 to both sides. Okay, I don't know what happened there. Let me try this again. We're going to add 32 to both sides of the equation. And so what I have is 9x squared, and I'm going to partner this x squared with another x, which actually I don't see. So I won't partner it, but I'll have plus 4y squared plus 8y, and I'm going to leave a gap because this is going to be a trinomial. So I'll leave a space equals 32. That goes away. And so now I'm going to follow my 4 steps for completing the square. The first thing I'm going to do is I'm going to divide out the a. Now for the 9x squared, I have nothing to divide out. There's no other term, so I can leave that one alone. I can just leave that as 9x squared. But over here, I'm going to say I'm going to divide out the a of 4, which means this is going to divide it by 4 right there. So it's going to be plus 4 times y squared plus 2y, gap equals 32, and I need to have this extra space right here. So I guess I should have put this plus a blank because I'm going to add a number there. I need to add something out here. So we're going to add something in right here. Okay, so now that was step 1. Now step 2 is we divide our b by 2. So I'm going to come to my b and divide that by 2. So positive 2 divided by 2 is a plus 1. And so what does that mean? Well, I'm going to come down to step 3. Step 3 is that I square that b divided by 2. And so I'm going to square this value here. Negative or positive 1 times positive 1 is a 1. That goes there. Now before I put a 1 there, it's actually going to be 4 times the 1. So I need to put 4 times 1. And this takes me to step number 4. I'm going to simplify. So what do I have here? I have 9x squared plus 4 times, and this is a perfect square. Factors of 1 that add up to 2 would be 1 and 1. And so it'd be y plus 1 times y plus 1, which is y plus 1 squared. And all of this would equal 32 plus 4 times 1, which is 32 plus 4, 36. Now, this, to simplify, I need to set this equal to 1. And so I would divide everything by 36. Now, the reason I know this isn't a circle this time is because these two numbers are different. The coefficients are different. So when I divide by 36 here, I'll find out that this is an ellipse. And 9 goes into 36 4 times. So this is x squared over 4. And by the way, you could just type in 9 divided by 36 into Desmos and press the fraction and see that it is 1/4. And so you have x squared over 4. 4 goes into 36 9 times. So it'd be y plus 1 quantity squared over 9 equals 1. That's my equation right there. And I'll go ahead and state this is an ellipse because it's not going to be circular, it's going to be stretched. So this is an ellipse. That's my equation on part A here. Let's try part B. So at this time I'm looking at it, I can tell you already it's going to be a parabola because I only have one term squared. So if you only have one term squared, what you're going to want to do is get the x's and y's separated. Because if you remember, let's go back over here on the formula chart, the x's and y's do not go together on a parabola. So there's a couple things I'm actually going to separate, not only the x and y's, but I want the single number, this constant of 16, to be with a non-squared term. So what I'm going to do is my pre-step is I'm going to subtract 16 from both sides, and I'm also going to add 4y. Oops, forgot the 4. And that's not the order I'm going to write it in, but that is, we will have x squared plus 4x, and I'm going to leave a gap here, equals, and I'm going to have my 4y minus 16 plus some value there. So I did my pre-step, and now I'll do the same 4 steps. So we first divide by a. So this problem is easy. It's 1, so I don't even have to really do anything. So I go on to step 2. And this is where we take our b and divide it by 2. So I'm going to take positive 4 and divide it by 2, which equals positive 2. Step 3 says you take that value, that b divided by 2, and you square it. So I'm going to take the positive 2 and square it, which means I have a plus 4 there and a plus 4 right there. There's nothing to multiply with, so it's just a 4. Finally, step 4 says to simplify. And so this is a perfect square. Factors of 4 that add up to 4 are 2 and 2. 2 and 2. So it'd just be x plus 2 quantity squared equals 4y. Minus 16 plus 4 is minus 12. But we're not quite done. That 4p, we need to get that outside of a parenthesis here. I need to factor this out. Technically, it's like a GCF, so I need to put a parenthesis there and divide that by 4. And so that's what I'm doing here now. Part of simplifying is the greatest common factor. And so I get my actual equation, x plus 2 quantity squared equals 4 times y minus 3. This right here is a parabola. Now part C, let's try it one more time. I notice I have 2 squares, which means it's not going to be a parabola. So I'm going to solve it as if it's an ellipse or a circle, which means I'm going to get this single number by itself on the right side and keep the x's and y's together. So I have x squared, and I'll add the 2x here, and I'll leave a gap. And then I have a y squared minus 6y, and I'll leave a gap. And all of this will equal 6. That was my pre-step. All right, step 1 would be divide by a. Again, my a's are 1, so I don't even have to do step 1. So that leads into step 2. Whoops. Step 2 is you take the b and divide it by 2. So I'll take this b, divide that by 2. And over here, I'll do the same thing. Take this negative 6 and divide that by 2. Step 3 is I'm going to square the b divided by 2. So this gets squared. It goes right here, which 1 times 1 is 1. And I need to add that on this side, plus that 1. And I also square this one. Negative 3 times negative 3 is a positive 9. So I add a 9 as well. Step 4 says simplify. So this front trinomial is going to simplify. Factors of 1 that add to 2 are 1 and 1. So it's going to be x plus 1 quantity squared. Over here, this trinomial Factors of 9 that add to -6 are -3 and -3. So this will factor to be y minus 3 quantity squared. All this will equal 6 plus 1, which is 7, plus 9 more is 16. Said another way, 6 plus, that's 10. 6 plus 10 is 16. This is a circle. There's no coefficients out in front, so this is x plus 1 quantity squared plus y minus 3 quantity squared equals radius squared. So the radius would be 4. That is a circle with a radius 4. That's what that shape is there. Now, you've seen me do algebra now 3 times in a row. You could have just typed these into Desmos to see the image of the picture and to solve from there. Also, if you use, in particular, my conics graph, conic sections, where is it? Conic sections, general form. If you use this, not only could you determine the shapes, but the equations as well. Let's just take A, for example. If I graph this one, I have 9x squared, so I have 9x squareds. I have 4y squareds. Let's change that to 4. This goes to y squareds. I have 8 y's, so E is y, 8 y's. By the way, I did not have any xy's, so it needs to stay 0. See, x's I think was 2. No, I didn't have any x's, so that's going to be a 0. And then I have a -32 on its own. -32 on its own, that's what f is. And you can see this is an ellipse here, just like we had. And if I click the key attributes, how we could compare this is you see the x squared's by itself because the h is 0, but the y becomes +1 because the k is -1. It's a liar when it goes inside the parenthesis. The a value, that's the larger term squared, should be 9. 3 squared is 9. B, you square the 2, you get 4. That's the smaller value. From the picture, we can tell that it is vertical, so the larger number goes under y, x, so on. So you could have done this on all 3 of the problems to solve, which means you can do it on this problem to solve this. Your DOL number 5. All right, let's take a look at these ACP problems. So it says an ellipse is centered at 3, -4. That's talking about h and k right here. H and k is 3, -4. And if you look at your problem, sometimes you can eliminate a problem just knowing the inside lies and seeing if any of those eliminate, which on this case, nothing does. And it says it has a horizontal major axis of 22 units. Now, the key for you is if you see major axis, I want you to think 2a. So 2a equals 22, which means 1a, you divide this by 2, equals 11. So in our problem, the largest denominator will be a squared. 11 times 11 is 121. So the largest will be 121, which eliminates answer choice B and answer choice C. So it's going to be either A or D. And it has an eccentricity of 0.72. That means that if our eccentricity is C divided by A, again, that's on the formula chart, then 0.72 repeating equals C divided by 11. So I'll go to my calculator here, and I just want to get a blank one here. So 11 times 0.727272 repeating. We can see that that's getting closer and closer as I do this to the number 8. So C is 8. And I can do this, but it is actually 8. But I'll do the approximately. So that is 8. Okay, so how do I find, it says, what's the equation of the ellipse? Well, the only thing I'm really missing is what is my B value? And I'll give you a hint, I'm looking for B squared. It's probably not going to be this one. I'm going to go ahead and guess this number because that is C squared and we need to B squared. Let's just check though. We know A is 11. So it follows the relationship from the formula chart. C squared equals A squared minus B squared. And so if I plug in my numbers, 8 squared equals 11 squared minus B squared. 8 squared is 64. 11 squared is 121. So 8 squared, which is 64, minus 121 or 11 squared, whoops, is negative 57. And so negative 57 equals negative b squared. That means positive b squared equals positive 57. And so that was correct right there. That was incorrect there. All right, and then number 2. An ellipse has vertices at 17, negative 1, and negative 13, negative 1. Okay, so let's just think about this here. I'm going to shift it a little bit this way, my graph. I got to go all the way out 17 units. Let's just say that right there, 17 units. And we got to go down 1. And so there's a vertice, and the other one is left 13. Let's just say that's negative 13 there. And so we have our other vertice here. Well, what I can tell right from the start is I can find out that if this vertice is 13 left and this vertice is 17 right, that's a total distance of 30. So the major axis is a length 30, or the A is half of that. So if the major axis equals 30, then 2A equals 30, meaning A is 15. And I can now say the center would be 15 to the right. So or from the left from that one. So it'll probably be easier to subtract. 17 minus 15 is 2. So we'll just say that's the center right there at 2. So the center would be right 2, down 1. That's the center. Okay, what does the problem even ask us though? It says the eccentricity is 0.6. So if the formula is this, that means 0.6 equals C divided by our A, which we found as 15. What is the value of B? Okay, so that's what we had to find. So I was just doing extra there, apparently. When I multiply by 15 here, we'll find out what C is. So 15 times 0.6 is 9. So C equals 9. And so now if I use my formula, C squared equals A squared minus B squared, we can plug in our values. 9 squared will equal A squared, 15 squared minus B squared. When I subtract my B squared, or my A squared rather, we will find out, let's see, what is 81, which is 9 squared, minus 225, which is 15 squared. That's negative 144. If B equals, or excuse me, if negative B squared, so negative 144 equals negative B squared, that means positive B squared equals 144, or B equals 12. That's the square root of 144. 12 would be the answer here. Let's make sure I get this credit by bubbling 1, 2.